In this video, we will look at one-to-one functions and inverse functions. So if you look at the top, it says recall there are 5 ways to represent a function. I have them listed here. The first one is as a set of ordered pairs. You see right here the set F. As a correspondence or mapping where you have the domain, which is the x's, and the range, which are the y's, and they are mapped to each other. As a table, you're used to that, an xy table. As a graph, you're used to that, or as an equation. What we're going to look at right now is the definition of a unique kind of function. And let's first remember that a function is a unique kind of relation. So what you have a relation, and then under that, you have special kinds of relations which are called functions. And under that, we have special kinds of functions that are said to be one-to-one. And that's what we're going to look at right now. So to define a function as one-to-one, it says a function in which each y value corresponds to exactly one x value is called one-to-one. Well, the way we defined a function was for every x value, you only had one y. This is just the opposite. So if we look at this, let's first check each of these examples and let's see if it's a function first. So does every x only go to one y? Yes. So it is a function. Now, does every y only have one x? Does it only correspond to one x? Yes, it does. So it is also one-to-one. All right, let's look at another one. In this one, we have our x's going to y's corresponding. Does every x only go to one y? Yes, so it is a function. But does every y only go to one x? No, this y goes to 2. So it is not one-to-one. On this last one, you can see that x sub 1 goes to 2 different y's. So this one is not even a function. So it can't be one-to-one because it's not a function to begin with. This one x goes 2 places. So there's an example of a function that is one-to-one, a function that is not one-to-one, and then an example of something that is not a function. All right, looking at our next page, we're actually going to determine if these examples are one-to-one functions. So it's already been given that they are functions. Every x only goes to one y. So for the following function, the domain represents the age of 5 different males, and the range represents their HDL cholesterol. So we want to know, is this function one-to-one? In other words, does every y only have one x? Well, as soon as you look at this y, it has 2 x's. So no, it is not one-to-one. It's still a function, but it's not a one-to-one function. All right, let's look at the next one. It's given as a set. I'm going to change it to a mapping because it's much easier to see. It's much more visual. So my x's are -2, -1, 0, 1, and 2. That didn't come out very clear. And my y's are 6, 3, 2, 5, and 8. I got to squeeze that in. I should have made my circles bigger. So -2 goes to 6, -1 goes to 3, 0 goes to 2, 1 goes to 5, and 2 goes to 8. First off, it's definitely a function. Does every y only go to one x? Yes. So this one is one-to-one. Every y only goes to one x. Now, here's an interesting example because it's a graph. The way we test if something is a function is we do what we call the vertical line test. You've had that before. You just drop a vertical line. If it only crosses in one place, it is a function. So yes, this one fits. Well, the way you check to see if a function is one-to-one is you do a horizontal line test. So let's do that with a different color. There's the horizontal line test. If it only crosses in one place, then it's one-to-one, and you can see that this one is not. So this one is not 1-to-1 because it crosses our graph in two places. So to check for a function, you do a vertical line test. To check if it's 1-to-1, you do a horizontal. And that is explained right here. All right, let's look at example 2. It says for each function, use the graph to determine whether the function is 1-to-1. And these are ones that we learned when we learned the library of functions. So we have f of x equals x squared. We know that that graph looks like this. Just to prove, I'm going to do both of these. I'll use two different colors. To prove it's a function, I do a vertical line. Yes, it is a function. It only crossed in one place. To see if it is 1-to-1, I'm going to do a horizontal line. It crosses in two places. So no, it is not 1-to-1. It's not that special kind of function. Let's look at the next one. G of x equals x cubed. So that one looks something like this when you graph it. It should be symmetric, but mine isn't. If we want to check and see if it's a function here with my red pen, yes, it is a function. And now if we want to check to see if it is 1-to-1 with the blue pen, I'm going to do a horizontal line. Now don't count where it crosses this vertical line, just count where it crosses the graph. It only crossed in one place. So yes, it is 1-to-1. So this one is both. So you can use those vertical and horizontal line tests for testing when you are given a graph. All right, let's look at the next page. This is a different type of function called an inverse function. This is a little bit more complicated than just the 1-to-1 functions, which are pretty simple. So the definition of an inverse function, it says suppose f is a 1-to-1 function. So first it's got to be 1-to-1. If the function f is the set of ordered pairs x, y, then the inverse of that 1-to-1 function is the set of ordered pairs y, x. So it's just the opposite. And the symbol that is used to denote the inverse of f is f like that. It's read f inverse, not f to the -1. It's f inverse. Now this is really important, this star. Let's go back. The function is xy. This is the function. Its inverse, let me get this on the screen so you can see it. Its inverse is yx, so the domain of the function, is the range of the inverse. And the range of the function, the y's, is the domain of the inverse. They're just opposite. So let's take a look. I think you're going to see the beginning of this to be easier than it sounds. So it says find the inverse of the following 1-to-1 function. And here it is listed. So f inverse is the set. And we're going to take each of these ordered pairs and we're just going to turn them around. So what was -3, -27 becomes -27, -3. -2, -8 becomes this. We continue. This one stayed the same because when I turn them around, they're the same. This one stayed the same. This one stayed the same. But this one turned around is 8, 2. And this one turned around is 27, 3. So the inverse, every x here becomes the y, and every y here becomes the x. Very simple. It says here that the inverse of f of x is x, and the function, the composite function of f inverse is x. Now this is confusing, so I want to do an example to kind of show you what this actually means, because this is actually really important. Remember in another section we did composite functions. We would do f of g of x. Well, what we're saying here is if you do f of f inverse of x, you will get x. And if you do f inverse of f of x, you will also get x. So this next example says verify that the inverse g of x, the inverse of g of x equals x cubed is g inverse is the cube root of x. So what we're going to do to verify that, this is kind of working backwards. We're saying that these two are inverse functions of each other. How can you prove it? You prove it by doing this, what I showed right here. You take the composite of each of them in both directions and see if it's equal to x. So I'll do it in two different colors to help you see. So the first thing I want to do is I want the composite g of g inverse of x, which would be g of g inverse is cube root of x, which means when I go to my g function, everywhere there's an x, I'm going to put in this. So that's going to be equal to the cube root of x, that's what I replaced, then cubed, and we know that cubing and taking the cube root undo each other and we just get x. So it checks in that direction. Let's check it in the other direction. Let's take the composite g inverse of g of x, which means g inverse of x cubed, which means go to my g inverse function and wherever you have an x, we're going to put in this. So that's going to be cube root of, take out the x, put in x cubed. They still undo each other. They still check. So that proves that yes, those two functions that you were given really are inverses of each other. All right, we're going to do the same thing on this one. Verify that the inverse of f of x equals 2x plus 3 is, and then we have this. So we're going to do the composite in both directions. So we're first going to do f of f inverse of x, which is f of, here's it, of 1/2 x minus 3, which means everywhere I have an x in the f equation, I'm going to put in this. So this is a little bit more complicated. So we start out and we write the 2. Take out that x, put in this. So I'm going to go 1/2 x minus 3 and then plus 3. So I just finished that. Those will cross cancel. That gives me x minus 3 plus 3, which is just x, which is what it's supposed to be. Let's do it in the other direction and make sure it works. Now we want the composite of f inverse of f of x. So that means f inverse of f of x is 2x plus 3. So what does that mean? It means go to my inverse equation, and everywhere there is an x, I'm going to put in this. So we start by writing 1/2 parentheses, take out the x, put in this whole thing, 2x plus 3. Now finish it, minus 3. That gives me 1/2 of 2x, which is just x, and it checks in that direction also. So you need to be able to do that. You need to be able to verify that two functions are inverses of each other by taking their composite in both directions and showing that they are both equal to x. All right, the next one says, obtain the graph of the inverse function from the graph of the function. So the graph of a function f and the graph of its inverse are symmetric with respect to the line y equals x. And I see an error here. This should be minus, and I think it just didn't come out. Maybe it's there and it's kind of embedded in that f. So let's look at what we're talking about on this next page. So in example 6, it says the graph shown below is that of a one-to-one function. So this graph here is a one-to-one function, okay? We want to draw the graph of its inverse. And then we want to draw the graph of the line y equals x. All right, so here I have this set up for you. So the points for f of x, we have -1, 0. That's this point right here. We have -2, -1. That's the point right there. Oops, I didn't mean to write on that. We have 2, 1. That's the point right here. So this purple is the function, the original function. So what I'm going to do in blue is I'm going to turn these around. I'm sorry I wrote on this. It was -2, -1. So the point becomes, for the inverse, f inverse of x, it becomes -1, -2. I just turned them around. This becomes 0, -1, and this becomes 1, 2. Now let's graph those. -1, -2 is the point that's right here. 0, -1 is right here, and 1, 2 is right here. And if I connect those, it looks like this. And you can see that those are actually reflections of each other across the line. This is the line y equals x going through the origin. So they're just, it's like it's just flipped over that line. That's what inverse functions are. They're reflections of each other across the line y equals x. All right, in this next one, we are going to look at, this is what we're going to spend most of our time on in this section, finding the inverse of a function if you are given the equation. So here's the procedure. There are 3 steps. So if you are given a function and it says f of x equals something, the first thing you're going to do is change f of x to y. That's the first thing. Step 2, you're going to switch the variables. So the y becomes an x and the x becomes a y. And then step 3 is you're going to solve for your new y. So let's just do one. It'll be easier to see it if we just jump in and do it. So we have the function f of x equals 2x plus 3. We are supposed to find the inverse and then find the domain and range of both of them and then graph both of them on the same coordinate plane. So let's start with f of x equals 2x plus 3. Step 1 tells us to change the f of x to a y. Y equals 2x plus 3. Step 2 says switch the variables. So the y becomes an x, the x becomes a y. You just switch them. And step 3 says now solve for y. And I'm going to solve for y by subtracting a 3. 2y equals x minus 3. And now I'm going to divide by 2, and I get y equals x minus 3 over 2, which is also f inverse of x. So there is the inverse by following those 3 easy steps. Now what we're going to do is I'm going to create, I may have to move this paper up just a little bit. I'm going to create 2 xy tables. I'll do x, f of x, that was our original, and then in blue I will do x and then f inverse of x. So let's just do our original function, which was back up here, 2x plus 3. So let's let x be 0. If x is 0, I'm just picking values so I can get a graph. If x is 0, that would give me 2 times 0 plus 3, or just f of x is 3. Let's try 1. That would be 2 times 1 plus 3, or 2 plus 3 is 5. Let's try negative 1. That would be 2 times negative 1 plus 3, or negative 2 plus 3, which is positive 1. Let's just try 3. If x was 3, I would have 2 times 3 plus 3, or 6 plus 3 is 9. I could pick all kinds of random numbers, okay? Now remember, this was the x and this is the y. So what I want to do when I go over to the blue side, my y's from here become my x's here. So I'm going to use 3, 5, 1, and 9. 3, 5, 1, and 9, because remember that's what an inverse is. But now I have to plug those numbers in. I can't just write 0, 1, negative 1, and 3, can I? We're going to see. When we plug these in to f inverse, I think you will see. So if I plug in x is 3, I would have, now I'm using the inverse, y equals 3 minus 3 over 2, which is 0 over 2, which is 0. And it looks like these are going to just switch. Let's verify it with one more before we jump to that conclusion. Let's let x be 5. So that would be y equals 5 minus 3 over 2, which is 2 over 2, which is 1. And yes, they are going to just reverse. Now I'm going to put those on my graph. Let me see if I can get this all on here at once. There we go. So let's do the purple one first. I have the point 0, 1, 2, 3. That's right here. I have the point 1, 1, 2, 3, 4, 5. I'm not going to be able to get that 9 one on here, but that's okay. I have the point -1, 1, which is right here. This is a straight line. It's linear. It goes through here. This is my f of x. All right. In blue, let's do our inverse. We have the point 3, 0. We have the point 5, 1, which is about right there. I have the point 1, -1. I don't need to do the 9, 3. And you can see this line goes like this, and in fact, if I had made my purple one longer, you would see that they eventually intersect down there. Now, remember what we said up at the top of the page when we were looking at this graph. A function and its inverse should be symmetric across the line y equals x. So if I now graph the line y equals x, you can see that that is true. It's a reflection across that line. Let me label this one. This is f inverse of x. So when we talk about the domain and range, we know that the domain for f of x is equal to the range of f inverse of x. And since they're linear, it's all real numbers. The sign for all real numbers is this. I'm going to use that symbol. And the domain of f inverse of x is equal to the range of f of x, which is also all real numbers. There's no restrictions on either one of those. Even though there is a denominator on f inverse, there's no variable in the denominator. So that is how you show an inverse and go through those steps. So let's try that again on one that is a little bit more difficult. So here in example 8, it says the function f of x equals 2x plus 1 over x minus 1 is 1 to 1. By the way, we have to say this so that we don't have a 0 down here. Find its inverse and check the result. How do we check the result? We show the composite in both directions are equal to x. All right, so here we go. The first step is to take out that f of x and put a y. So that is y equals 2x plus 1 over x minus 1. Step 2 is wherever you have a y, you put an x. Wherever you have an x, you put a y. So I ended up with 2 y's on this side. Now before I can go any further, I have to get rid of this denominator by multiplying both sides by the LCD of y minus 1. Distributing here, it's going to give me xy minus x. Here, I'm going to have 2y plus 1. Now, what do we do when we want to solve for a variable and there are 2 of them? What you do is you get them on the same side of the equation with everything else on the other side. So I'm going to add an x to both sides, and I have xy equals 2y plus 1 plus x, and now I'm going to subtract a 2y. And that gives me xy minus 2y equals x plus 1. Now how do I go from having 2 to having just 1? You factor out the one that you are looking for. Y times x minus 2 equals x plus 1. And now the only step left is to divide by that. And I get y equals x plus 1 over x minus 2. And that is the inverse function. And you are going to have to be able to do that. So make sure you understand that. Now we have to verify that that works. So I have to do, and this is going to take some space. I hope I've got space here. If not, I'll use another sheet of paper. We want to check. So I need the composite. Let's first say what is f of f inverse of x. That means f of x plus 1 over x minus 2. Well, go to the f equation. Everywhere there's an x, I'm going to put in this. It's going to be quite messy. So that's going to give me, remember, go to this, 2, take out that x and put in x plus 1 over x minus 2, and then plus 1 all over, here's another x, take it out, x plus 1 over x minus 2, and then minus 1. Lot going on there. How do I get rid of these denominators with this complex fraction? I multiply everything by the LCD. Everything meaning I multiply every term. So this gets multiplied by x minus 2. This one gets multiplied by x minus 2. This gets multiplied by x minus 2. And so does that. And I'm going to need another sheet of paper. I can see it right now. So this cross cancels this. I'm left with 2 times x plus 1 plus, distribute the 1, x minus 2 all over x plus 1. Now distribute that negative 1 minus x plus 2 in that denominator. X's go away. In the numerator, I have 2x plus 2 plus x minus 2 over 1 and 2 is 3, or 2x and x is 3x over 3, because my 2's go away, which is just x. So it checked in that direction. Let me get another sheet of paper, and we will check it in the other direction. I'll try to do it right underneath here so you can see. Now let's do the composite in the other direction. So let's do f inverse of f of x. So that means f inverse of, what is f of x? 2x plus 1 over x minus 1. So what does that mean? It means go to the f inverse equation right here, and everywhere there's an x, we're going to put in this. So that's going to give me 2x plus 1 over x minus 1, and then plus 1 over, here's another one of those x's, 2x plus 1 over x minus 1, and then minus 2. Let's put each term in parentheses because I need to get rid of those denominators by multiplying by the LCD, which is x minus 1. Those cross cancel, and I am left with here, in my numerator, 2x plus 1, and distribute that, plus x minus 1 over 2x plus 1. Now distribute the negative 2. Minus 2x plus 2. That's a 3x. Here I have a 2x minus 2x over 3, which is x. It checks in that direction, but that was not an easy task to do that. Let's do one more of those. I know, you're thrilled, right? All right, example 9. Here we have a function x plus 2 cubed minus 1. It's 1 to 1. We want to find its inverse. So step 1, replace f of x with y. Y equals x plus 2 cubed minus 1. Step 2, take out the y, put in an x, take out the x, put in a y. Step 3, solve for y. Well, I need to isolate what's been cubed first, so I'm going to add a 1. I get x plus 1 equals y plus 2 cubed, and now to get rid of that, I'm going to take the cube root of both sides. I'm taking the cube root of this side and the cube root of that side. That gives me cube root of x plus 1. Those undo each other, equals y plus 2, and now all I need to do is subtract a 2, and that gives me y equals cube root of x plus 1, and then outside of the radical is this minus 2. So there's my inverse function. Remember, this is also f inverse. Okay, now to check it, I'll do one of them here and then the other one on that other sheet. To check it, I want to do the composite in both directions. So let me use my colors again. So let's use our purple first, and we're going to take f of f inverse of x. So that means f of this, cube root of x plus 1 minus 2. That means I go to my f function, which is this, and everywhere there's an x, I put in this. So it's going to be equal to, just continue down here so you can see. I go to this, take out that x, put in this, cube root of x plus 1 minus 2, then plus 2, and then cubed. Well, those just go away. That's equal to cube root of x plus 1 cubed, and the cube root, and I missed a minus 1 somewhere. Oops, I missed this minus 1. Sorry, there's a minus 1 on the end there. Minus 1. Cube root of x cubed, or cube root of x plus 1 cubed is x plus 1, and then we have this minus 1. See where I missed it? Right there. I missed it on the original function. Just gives me x. So that checks, and I actually think we have room on here for the other way. So now let's go the other direction. F inverse of f of x means f inverse of, I'm going to write it right this time, x plus 2 cubed minus 1, which means go to the inverse function. Everywhere there's an x, write this. So that's going to be cube root of, take out that x and put in this, x plus 2 cubed minus 1, and then plus 1, and then minus 2 out here. Whoops. Sorry, I didn't mean to extend that. That minus 2 is out here. So this went into place for this. So there was still a plus 1, and then the minus 2 on the outside. Those just go away. The cube root of x plus 2 cubed is just x plus 2, and then that minus 2 gives me an x, and it checks that direction. These are not easy because you can get very, very lost in the algebra of it. So on your own, I want you to try this one. Stop this recording, this video, and try this one on your own, and then come back on and check yourself. I'm assuming you've already tried this now on your own. So let's check. You should have replaced y equals 2x over 3x minus 1. Switch them. X equals 2y over 3y minus 1. Multiply by the LCD, 3y minus 1. Distribute here. So 3xy minus x equals 2y. We want to get our terms that contain a y on the same side. So I'm going to add an x. 3xy equals 2y plus x. Subtract the 2y because we're trying to solve for y. 3xy minus 2y equals x. Now factor out that y. 3x minus 2 equals x. And divide by what's left, 3x minus 2. And I get y equals x over 3x minus 2. That is my f inverse of x. That's what you should have gotten. Let's do the check on the next page on that sheet that I used because I don't have room here. So to check it, we first want to take f of f inverse of x. So f of f inverse of x. Well, that means f of our inverse is x over 3x minus 2. Well, that means go back to the f function, the original function, which I'm going to write up here. It was f equals 2x over 3x minus 1. And everywhere you have an x, you're going to put in this. So you got to be careful how you write it. It's going to be 2. That's this 2. Take out this x, put in this. X over 3x minus 2. That is all over 3. Take out the x, put in this. X over 3x minus 2 minus 1. So I need to get rid of those complex fractions. So I'm going to multiply everything by 3x minus 2. This is over 1. This gets multiplied by 3x minus 2, and this whole thing here, just like this one, whole thing, gets multiplied by 3x minus 2. That cross cancels, and I'm left with a 2x in the numerator, just a 2x in that numerator. And then in the denominator, this cross cancels this, and I'm left with a 3x. Now distribute the negative 1, minus 3x plus 2, which is 2x over 2, which is x. It checked in that direction. Let's check it in the other direction. So in the other direction, what we want, in the composite, we want f inverse of f of x. That means f inverse of this, 2x over 3x minus 1, which means now we go to the inverse equation. F inverse was equal to x over 3x minus 2. And everywhere there's an x, we're going to put in this. So that's going to be an x on the top, so 2x over 3x minus 1, over 3 times this, 2x over 3x minus 1, minus 2. I still have to get rid of that complex fraction. So I'm going to multiply by the LCD on each one. I'm going to multiply this term by 3x minus 1 and this term by 3x minus 1. You really got to know what you're doing with complex fractions here. And you left in the numerator with a 2x. Let's see down here, it's a little more complicated. I have 3 times 2x is 6x. Now distribute the negative 2 minus 6x plus 2, which is 2x over 2, which is x, and it checks.